Let's next consider the rotation and distortion of fluid elements when it flows. Let a rectangular fluid element on the left inside a moving fluid move after a time delta t to the location shown on the right. As you see, it has changed its shape. Let's assume it is not rotating or deforming. Now, if we consider the leftmost lower edge of the fluid element, in time delta t, it would have moved at distance u delta t, and the rightmost element on this line would have moved a distance u plus delta u by delta x into delta x times delta t. The velocity of the point on the right side is going to be a little different from the velocity at the left end, and the velocity at the right end is found by Taylor's expansion. Clearly, this would mean that the horizontal line at the bottom of the fluid element is now stretched. This is the original size of the fluid element, and this stretch is nothing but the difference of the two motions, and that would be delta u by delta x into delta x times delta t. This is the stretch introduced. So what is the strain introduced? Divided by delta x. And what is the rate of strain? Divide again by delta t. So delta u by delta x is the rate of strain in the x direction, the linear strain rate in the x direction. Similarly, we can find in other directions. In the y direction, it will be dv by dy, and so the volumetric strain rate in two dimensions would be the current volume, which is 1 plus delta u by delta x into 1 plus delta v by delta y, minus the original volume, and so this is du by dx plus dv by dy. This is the volumetric strain rate. Now, if the fluid is incompressible, then delta u by delta x plus delta v by delta y should be 0. This is the famous continuity equation for incompressible flows that we will discuss in the next lecture. Let us further consider rotation of this fluid element. Let this be a fluid element of size delta x and delta y at time t, and after time delta t, let the fluid element occupy this position. This element would translate also, would have brought it back so that the left bottom point is coinciding. So we removed the translation in x and y direction. We are worried only about rotation. The bottom rightmost point has moved up relative to its original position, and that's because of the velocity gradient, because the difference of v velocity in the x direction. So this height in time delta t would be delta v by delta x into delta x by delta t, and therefore the angle through which the horizontal line rotates is dv by dx into delta t in time delta t. Similarly, the vertical line rotates counterclockwise by an amount minus delta u by delta y into delta t in time delta t. The average rotation of the element is obtained by taking the average of these two rotations and the rate of rotation of the element omega z is 1/2 delta v by delta x minus delta u by delta y. Those of you who are familiar with vector calculus would recognize that delta v by delta x minus delta u by delta y is nothing but curl of velocity, del cross v vector. So the rate of rotation omega z is 1/2 of the curl of velocity. We will be using this fact later. This rotation of the fluid element, curl of v, which is twice the rate of rotation, is also termed vorticity as a measure of rotation of the fluid element. Here we have shown a fluid element that rotates as it moves along its path line. The rotation is recognized by treating this fluid element or representing this fluid element with two lines crossing one another, and one of the line carries an arrowhead. And so clearly we can see the particle is rotating as it moves along its path line. In a channel, if the upper plate is moving with the velocity v naught and the lower plate is stationary, we have seen earlier that there is a velocity profile. The velocity is large near the upper plate and it tapers down to zero velocity at the bottom plate. A rectangular fluid element is now distorted. Also, as seen by a sequence of arrows on the top, the upper end of the vertical arrow is moving faster than the lower end. So this arrow rotates clockwise. So this flow is rotational. There is vorticity in the flow. The flow itself doesn't have to move along a circular or a curved streamline or a path line. The path lines are straight. The rotation here refers to the rotation of fluid elements about their own axis. It has nothing to do with rotating path lines. In fact, we can show, and we will show later on, that if the velocity is like k by r, the velocity in a free vortex or the velocity in a model hurricane or a tornado, the velocity decreases as r increases linearly, and we can show that even though the particles are moving in circular path, each fluid element is not rotating. The two gray areas we have shown, the diagonals have the same orientation at two locations, signifying that the fluid is irrotational. There is no vorticity.
This gadget is a vorticity meter, which floats in water with its axis vertical. The two vanes at the bottom are driven by the angular velocities of two mutually perpendicular fluid lines. So the arrow at the top turns at a rate equal to the average of these two. That is, with half the vertical component of vorticity of the lump of water in which the vanes are immersed. This tank has been on the turntable for a long time, and viscosity has forced the water into a rigid body rotation. The vorticity float rotates almost exactly with the speed of the crossed white lines on the bottom of the tank. Sometimes the word rotation is used as a synonym for vorticity, but this does not mean that a flow has to be curved for vorticity to be present. Here, for instance, water flows in a straight channel. The streamlines are essentially straight and parallel to the side wall. But the arrow rotates, showing that vorticity is present.
The same picture we can invoke to explain distortion. Here, the x line, the horizontal line, has rotated through an angle dv by dx into delta t, while a vertical line has rotated through an angle minus du by dy into delta t, as explained before. The rotation of the fluid element was the average rotation. But what is the distortion? One side is moving counterclockwise, the other side is also moving counterclockwise. So we can find the distortion. We can find the distortion by subtracting the two rotation, and the rate of distortion per unit time is now given by 1/2 of dv by dx plus du by dy. This rate of distortion is the shear straining, and this shear straining causes shear stress. We had seen earlier when we had flow through a channel in which there was only one component of velocity u, which was a function of y. The rate of strain, the rate of distortion was just du by dy. In two-dimensional flow, this would be dv by dx plus du by dy. Let us now consider how do we analyze fluid flow. In solids as well as in fluids, the law of physics in the simplest forms apply to identified systems of matter. The law of conservation of mass, the momentum theorem, the law of conservation of energy are applicable only to a fixed and identified quantity of mass. But in fluid, as we have said before, we like to work with control volumes, with an Eulerian approach when we don't follow the material quantity. So what do we do? It is impossible to keep track of the systems in many fluid problems, or the boundary conditions are given in Eulerian description. We therefore prefer to work in Eulerian frame of reference. The laws are available in the Lagrangian frame of reference, so we need some tools to bridge the gap, i.e. work with the Eulerian description, yet use the laws available for systems or the Lagrangian description. System is a fixed mass of fluid. Its boundaries may change with time. In fluids, we work with control volumes. A control volume is a region in space. Mass can and usually does cross the boundaries of the volume. This control volume could also be moving in space, could also be changing its volume, but it is a volume that we will consider. when we apply the physical laws, we need the rates of change of material properties associated with the system. All physical laws that are available to us use the rate of change of material systems. But in fluid mechanics, we deal with control volumes, and the rate of change that we know are available for control volumes. So we need a relation between Eulerian rate of change and the material rates of change. To obtain the relation, consider a control volume with one inlet and one outlet. In time delta t, a volume of the fluid moves into the control volume, and the volume that moves in is V at the inlet times the area at the inlet times delta t. The mass that moves in is rho times the volume that moves in. And if the specific property, that is the property associated with unit mass, is eta, then the quantity of the property that is moved in is rho V in A in into delta T times eta at the inlet. This is the quantity that moves in. Similarly, a quantity would move out at the outlet in association with the fluid that moves out of the control volume. The volume moving out of the control volume would be V out delta T times the area at the outlet, and the property that moves in with this would be rho times eta times V at the outlet times A out the outlet times delta T. So that the change associated with the control volume would be delta n by delta T, the rate at which the n contained, the property n contained within the control volume changes, times delta T is equal to dn by dt, the material rate of property n associated with the volume of the control volume times delta T, plus the property that is moving in minus the property that is moving out. And so, if we divide by delta T, we get this relation. Delta n by delta T is equal to dn by dt plus rho A V eta at the inlet minus rho A V eta at the outlet. This is the net influx of n. And we can write this in an alternate form. dn by dt is equal to del n by del t plus the net outflux of n. This is known as the Reynolds transport theorem, and is a very useful theorem for analyzing the fluid flows. The rate of change of physical quantity associated with the system, the control mass, minus the rate at which it diffuses out of the system, equals the rate of production of that quantity within that system. That is how we write the conservation laws. The rate of change of physical quantity associated with the system minus the rate at which it diffuses out of the system is equal to the material rate of the system, of the quantity within the system, which is also equal to the rate of production of that quantity within the system. If that quantity were mass, the rate of production of that quantity is 0. If that quantity was momentum, the rate of production momentum is the net external force applied on the system. If the quantity was energy, the rate of production of that quantity within the system is equal to the net rate at which the work is done on the system minus the net rate at which the heat is lost by the system. The rate of change of physical quantity associated with the system is equal to the rate of accumulation plus the net efflux of the physical quantity. And this, we can write it like this. The rate of production of the quantity within the control volume minus the net convective efflux of physical quantity across the control surface is equal to the rate of change of physical quantity contained within the control volume. This is the local rate of change or the rate of accumulation plus the net diffusive flux of the control volume across the control surface. The first efflux, which is the second term on the left, is the physical quantity that moves out of the control volume in association with the mass crossing the boundaries of the system. While the diffusive flux, which is the second quantity on the right, is a quantity that crosses the control surface, not in association with the mass, but because of something like temperature difference. The energy may be losing because of temperature difference, diffusive loss. Mass is not lost diffusively, momentum is not lost diffusively, but the energy is lost diffusively. We apply this to a system in which we have a container in which the mass is coming in at the rate m1 dot, the mass is leaving at the rate m2 dot. The control volume is defined as the volume enclosed by broken line. The broken line itself represents the control surface. The rate of production of the quantity within the control volume is obviously 0. Net convective flux of the physical quantity across the control surface, convective across in association with the mass. So m1 dot is moving, m2 dot is moving out. So m2 dot minus m1 dot is the net efflux. And the rate of accumulation is dm by dt. M, capital M, is the mass contained within the control volume. The rate at which the mass contained within the control volume is changing is the rate of accumulation of mass, and the diffusive flux is 0. So clearly, the rate of accumulation is the rate at which the mass is in flux into system. Thank you very much.